Hi dear students. So in this section we will discuss about the escape velocity or the escape speed and as well the energy of the satellites. Also the two types of satellites that are the geostationary and the polar satellites. And as well we will discuss about the weightlessness also. So let us first of all discuss about the escape speed. As you all know, suppose if you are throwing a stone upward, it will fall back or it will come back to the surface of the earth. At the same time, if you are considering a rocket which we are launching or which we are sending to space, as it is moving upward, it is not falling back and it can even overcome the gravitational attractive force or the gravitational pull. The stone is coming back, it is because of the gravitational pull exerted by the earth upon that stone. As it is moving upward, the earth is pulling back the stone to the surface of earth. So this escape velocity or the escape speed is having something related with this pulling back force. So what it is? The minimum velocity or the minimum speed required for some particular body, maybe a satellite, maybe a rocket, whatever. So the minimum velocity required for a particular body to overcome this gravitational pull or this gravitational attractive force is known as the escape velocity. So if a particular body is having the minimum amount of that escape velocity, then it can go beyond the gravitational limit or the gravitational field. It means it can overcome and escape from that gravitational field. So escape velocity is required for a particular object to escape from the gravitational pull of the celestial body. Here we can consider the celestial body as the earth. Okay. Now, with the help of the concept of or the law of conservation of energy, we will deal or we will derive the expression for the minimum amount of the escape, minimum amount of the velocity or to overcome the gravitational pull, or it is known as the escape velocity. So considering we are sending a satellite to the space, but the point we are considering at the space, it is at an infinite distance from the center of the earth. And we are sending that satellite from a height h above the surface of earth. So it will be re plus h distance away from the center of the earth. So the initial point from where the particle or the body it is launching or sending, it is re plus h distance away from the center, and it is reaching an infinite distance. So we are considering the initial and final points, these 2 points, and we are comparing their energy values. Means according to the law of conservation of energy, the energy, total energy of that particular body initially will or should be equal to the total energy at the final point. So initial point at the first of all we are having the final point, that is it is represented as E infinite or E infinity. So here E infinity it is given as W1 plus mVf square by 2, where W1, that is total energy or total mechanical energy, that is actually the sum of the kinetic energy and the potential energy. Kinetic energy and potential energy. So here kinetic energy is mvf square by 2 and the potential energy it is W1. In the earlier section itself we have seen the potential energy at an infinite point will be 0, hence the W1 value will be 0. Now the remaining, that is the kinetic energy, that is mvf square by 2, where vf is the final velocity of that particular body when it reached the infinite point. So the total energy of that particular body at infinite distance it is W1 plus mvf square by 2, where W1 value it is 0, hence vf square by 2, mvf square by 2, that is the kinetic energy, and that will become the total energy. Now consider the initial point. So you are launching or you are sending that particular body or that satellite, consider a rocket or satellite. It is from a height h above from the surface of earth, so that is re plus h distance away from the center of the earth. So here kinetic energy plus potential energy you have to consider. The kinetic energy value will be half mvi square. M is the mass of that body, vi is the initial velocity of that particular body. So half of mvi square. Now the potential energy value, it is minus of g m into me divided by the distance from the center, that is h plus re, plus w1 it is the potential energy at the surface of earth. Here also this w1 value will be considered to be 0. So here the total energy will be half mvi square minus gm me divided by h plus re. Okay. So that is the total energy of the satellite at a height h from the surface of the earth. Otherwise we can say the initial total energy of the satellite. So now comparing or considering the conservation of energy, the law of conservation of energy, that is E at the energy at a height h plus re should be equal to the energy at a height or energy at an infinite point. So we can, comparing these two equations, you will obtain the equation as mvi square by 2 minus gm me divided by h plus re will be is equal to mvf square by 2. So just equating these two equations, the above two equations we are equating, and we will obtain the equation as mvi square by 2 minus gm divided by h plus re will be is equal to, that is initial total energy value will be is equal to the final total energy value. Now here one thing you have to note, that is mvf square by 2 value, that is the kinetic energy value at a point infinite should always greater than 0 or equal to 0. That energy value cannot be a negative value. Okay, so that will be always mvf square by 2 value should always be positive, or it should be, or it may be equal to, it might be 0. Then you can rewrite the LHS as, LHS will become, that is mvi square by 2 minus gm me divided by h plus re can also be greater than or equal to 0. As mvf square by 2 is greater than or is equal to 0, the LHS will be also become greater than or is equal to 0. Then taking the gme minus of gme m divided by h plus re term to the RHS, we can obtain the equation as half of m vi square greater than or equal to gme m divided by h plus re. Now this greater than or equal to signature, you can make that one as an equal signature, that is by applying the vi as a minimum value. When you are applying the vi minimum, the greater than or equal to sign will become equal signature, equal, that you can make that one as a equation. So half mvi square minimum will be is equal to g me divided by h plus re. So solving this one, you will obtain the vi minimum as root of 2 gme divided by re, where you know that g into me divided by re square, it is small g, that is the gravitational acceleration value. So you are multiplying and dividing the RHS of this equation with RE, okay, with RE inside the root. Inside the root, if you are multiplying and dividing with RE, that is root of 2g me RE divided by RE square will be there. So GME divided by RE square will become small g, that is the gravitational acceleration, and into RE, it is VI minimum. It is the minimum initial velocity required for one satellite to overcome the potential, overcome the gravitational field or the gravitational pull, is VI minimum, which can be represented by, or which can be given by the equation, that is VI minimum is equal to root 2g RE. By substituting the g and RE values of Earth, you can find out the value of the escape speed in the Earth, in the gravitational field of Earth is near to 11.4 kilometer per second. That is escape speed required. So the rockets are having greater than or equal to that speed. That's why they can overcome the gravitational pull and they can escape from the gravitational field of the Earth. Now coming to the Earth satellites. So as the planets are revolving around the Sun, the satellites of Earth or any planet, if you are considering another planet, the satellites are also revolving around a particular planet, where the planet will be at the center, and in the circular orbits the satellites are revolving or surrounding the planet. So in the case of the circular motion, you know that there will be a force acting towards the center, and that is known as the centripetal force. And if the velocity of the particle which is moving in the circular path of radius r, then the centripetal force value will be m. If the mass of the body, if it is m, then it is mv square divided by r. So that is the expression for the centripetal force. So here the gravitational force is acting, or it is providing the centripetal force. So centripetal force will be equal to the gravitational force value. Hence that is mv square. Suppose if you are considering the r means suppose if you are considering a point height, a distance h, the satellite is revolving around the planet h distance from the surface. That means the total distance, if the planet or Earth, consider Earth, then in the case of the Earth, the radius it is RE, hence RE plus H will be the total distance from the center to that planet. So mv square divided by RE plus H will be the centripetal force. And here the gravitational force, actually the gravitational force it is providing, the centripetal force. So you can equate the centripetal force with the gravitational force. Hence the gravitational force value, that is gm into me divided by RE plus H square. Comparing these two equations, you will get the v square value as gme divided by RE plus H. That is gma divided by RE plus H, which will be is equal to g into RE if the H it is comparably less. If the H value if it is comparably less, then v square will be is equal to g into RE. Then from this relation you can see the v square and h are inversely proportional to each other. Hence if v decreases, h increases, or h increases, v decreases, and as well h decreases, v increases. They are inversely proportional to each other. Now you are considering a satellite. Suppose this is the center portion of the Earth, a satellite which is revolving around the Earth, and the circular path it is having a radius of R E plus H. Then the circumference, the path which is covered will be having, the length of the path will be 2 pi into Re plus H, the circumference of the circle. So 2 pi into Re plus H, and for one complete circle, the time required for one complete circle or making from one complete circulation, it is T, that is a time period. So on the basis of these two values, that is the path covered, the length of the path covered, the distance covered, and the time for that traveling, or the time for that revolution, if it is T, then means we can find out that time period with the help of the velocity and the path covered. Suppose if the satellite or the planet which is moving with the velocity capital V, the T will be is equal to 2 pi into Re plus H divided by V. Now you can substitute the V value that we have derived in the previous slide. We have derived one V value, so we can substitute that one here. Then you can obtain the time period value as 2 pi into Re plus H all raised 3 by 2 divided by root of G into ME. And if you are squaring both sides of this equation, that is T square will become K into Re plus H all raised to 3, where this K value it is actually 4 pi square divided by G into ME. As well, if you are considering the H as 0, that means if we are considering the satellite is very close to Earth, then the T value will become T0, and the H value will be neglected. Then T0 value will become 2 pi into root of Re divided by G. You can substitute the values of Re and G, then you can obtain the value of T0 as 85 minutes. 85 minutes. 85 minutes it is the time required if the H is approximately equal to 0 or H is very much less than Re. Now let us come to the energy of an orbiting satellite. The energy, in the sense that you have to consider the potential and as well the kinetic energies. The kinetic energy you can obtain from the relation half mv square, mass and velocity, where velocity expression that you can obtain from the previous value, that is this v value, you can substitute. So half mv square, the v square value you are substituting, so you will obtain the kinetic energy as G m me divided by 2 into Re plus H. That is the kinetic energy value. As well, the potential energy value, that expression that we have already derived, that is potential energy will be minus of G into me divided by Re plus H. So as you have to find out the total energy, we have to take the summation of kinetic and as well the potential energy. So the total energy value will become minus of G m divided by 2 Re plus H. So here you can see the total energy is the negative of the kinetic energy and 1 by 2 times that of the potential energy. You should remember, you should study this relation. It will be applicable in the examination in some problems, as well in the competitive exams also you can apply this relation. So be familiar with this relation, okay? The potential energy and the kinetic energy and as well the total energy of an orbiting satellite. Now let us come to the various types of satellites, that is the geostationary and the polar satellites. Two types of satellites are there, geostationary and polar satellites. The geostationary satellites, which are having the same period of revolution or the period for as the period of rotation of the Earth. Earth about its own axis. That means the time period should be almost equal to 24 hours. And such satellites are known as the geostationary satellites, and If we are viewing a geostationary satellite from the surface of Earth, we will found that one as a stationary. It will always be upon one particular point of the Earth. It will be always collecting the data from one particular point. Another definition for the geostationary satellites are satellites in a circular orbit around the Earth in equatorial plane with t is equal to 24 hours. That is, the time period it is equal to 24 hours, and that is equal to the time period of the revolution of Earth on its own axis. And such satellites are known as the geostationary satellites. And you can find out the distance, Re plus H distance, at which height or at what height the geostationary satellites will be placed. That you can find out with the help of this equation, that is Re plus H is equal to T square of G into ME divided by 4 pi square all raised to 1 by 3. Where you have to substitute the T value as a 24 hours, and then you can find out the distance or the height above from surface of Earth where the geostationary satellites will work properly. Now, the geostationary satellites appearing fixed above the broadcasting station can receive these signals and broadcast them back to the wide area on Earth. So in the case of the radio transmission, the radio signal transmission, actually the ionospheres, the radio signals are having very less frequency, that you know. So when it is reaching the ionosphere, what will happen? It will be get scattered or reflected back, and it couldn't reach, the radio signals could not reach the receiver properly. So for solving that one, we can use this geostationary satellites. So satellites will absorb the radio waves and it will emit back the radio waves, means with a higher amplitude. They will just amplify the signal and then emit back, reflect back or emit back to the, transmit that to the receiver. Then without much noise or the data loss, we can receive the signal. The INSAT group of satellites set up by India are one of such geostationary satellites are widely used for the radio telecommunication in India. Now let us come to the next one, that is the polar satellites. As the name indicates, it is rotating or revolving around the polar regions. So polar satellites are low altitude. The height it is given, that is 500 to 800 kilometers satellites. They go around the poles of the Earth in the north-south direction. At that time, our Earth it is rotating in the west-east or east-west direction. So, and the time period value for these polar satellites are near about 100 minutes. So it crosses many times the polar regions. It crosses the polar region many times. And the camera fixed on such satellites can view only small strips of the Earth in one orbit. One orbit means in one rotation. So one complete strip will be obtained. Okay, thereafter, the adjacent strip values are viewed in the next orbit. On the next revolution, the adjacent portion will be the details from the data from the adjacent portion will be collected by the satellite. So that by completing a complete rotation, means one after another, likewise complete rotation means maybe or 10 or 15 rotations. After 10 or 15 rotations, the polar satellites will have cover the whole portion of the Earth. Means the whole portion of the Earth can be viewed strip by strip during the entire day. Not after 10 or 50 rotations. That means 24 hours. After 24 hours or after one day. By one day it will cover all the complete portion of the Earth, the polar satellites. At that time the geostationary satellites will be covering only a particular region. particular region only. And the major functioning, they are extremely useful for the sensing, the remote sensing, meteorology, and as well for the environmental studies. For these purposes, the polar satellites are using. Now the last one, that is weightlessness. Means you may have heard about the free falling. Actually, the mass and the weight. The weight, it is actually due to the gravitational acceleration. So mass into the gravitational acceleration value is actually the weight. So suppose if you are in a field where the gravitational acceleration value it is almost zero, then your weight will become your mass. That means weight will be, the effect of that weight will become zero. That is what the astronauts are felt. Astronauts are feeling the same thing, that is the weightlessness, when as they are reaching the space where the gravitational pull value or the gravitational acceleration value it is negligible. As a result, their weight will become less. It means weightlessness. They will feel the weightlessness. So when an object is in free fall, its weightlessness, and this phenomenon is usually called the phenomenon of weightlessness. Means without weight, weightlessness. And as well, in a satellite around the Earth, every part and parcel of the satellite has an acceleration towards the center of the Earth, which is extremely the value of Earth's acceleration. So as you are having, if you are moving with the Earth's acceleration value, that is 9.8 meter per second square freely, there shouldn't be any other forces. If you are moving freely with the same acceleration, then you will feel weightless. It means the satellites around the Earth, all the particles there inside the satellites having or experiencing, there is acceleration of 9.8 meter per second square, or the gravitational acceleration. That is, Earth is continuously pulling them towards it, or towards the center of the Earth with the gravitational acceleration g 9.8 meter per second square. As a result, the particles will almost, they are having the feeling of free falling. Okay, so they will feel, or they may feel the weightlessness. So these are the major things about this chapter. And go through that exercise question answers as well the example question answers, and as well read the textbook once thoroughly. If you are having any doubts, you can ask me. Okay then, thank you.